of the questions have some calculations, so it takes a little bit of time, and some others just like true and false, and it's just a statement. So just choose the answer, and this will be for 1 point. So I'm giving the one that has calculation more weight 2 points, and the one that does not have calculation it will be only one point. And I think, as I understand from the blackboard, that you have you when you answer one question, you cannot get back to it, and it will show one question by question. So you want to go fast a little bit, and the time will not be extended. It will be 20 minutes, no extension. So you have 10 questions. I think 4 of them for 2 points, and the rest 1 points. So 4 calculations, and the rest are just you choose the answer, just a statement there. So you will have a question, one question at a time, and once you finish this, you cannot go back to it. And so this is what I wanted to say here. Any comments? Is it understood what I mentioned? Is it clear?
Yes.
Okay.
Yes, Doctor.
Okay, very good. And of course, and while you are sitting at home, I'm preparing all the exam as if it is an open book exam. Because you have the book, you can reach whatever you want. I'm not using camera because I prepared the exam in this way. And therefore, of course, you should not use the book. I mean, you should know what is the materials that you have. You should study and then just answer right away. Book, or you should use a formula sheet just for things that you cannot memorize. But of course, if you are going to go through the book and read and study during the exam, of course, 20 minutes will be little time. Even 1 hour will be little time. You may need some days, and therefore the complaint will be the exam is long, because you study not to solve the exam. So I want you to study well, and therefore you can go to the exam without a need for a book, although it is an open book if you want. But open book here means that you studied everything. Just if you need a hint or something, then you can use the book or the formula sheet. So normally in such exams, there is a complaint the exam is long because some students are studying, not examining. So this is the first session. Regarding the midterm, and I will only give 20 minutes, and then I'll only the class will be 20 minutes. The rest of the class will be any questions you want to ask, or you want to go and study, whatever you want. For the midterm, it is problems to solve. As I mentioned, one problem in chapter 8 and 2 problems in chapter 9. Okay, so let me start. I have already 27 now, so most of them came. So let me start. Do you have any questions? Is it clear?
Doctor,
Yes, yes, Hassan.
for the calculation questions, will it be like a small problem or connected?
It is a small problem. Yeah. It is a small problem, not just small calculations, but it will take 2 minutes or 2 to 3 minutes, something like that. But it is very, very small. Yeah. I'm not going to give you a regeneration cycle or something like that. Yeah. Okay. But it has more weight. Oh, go ahead, Hassan.
I mean, thank you. It's clear now.
Okay. But it will have more points. So, so when you have such a problem, give it more time. When you have the other problem, give it less time. So everyone, as I mentioned here, the calculation problem will have 2 points, and the other statement will have 1 point. Okay, but I want you to go through all of them. So arrange your time to cover all of them. There are 10 questions. Any other questions you have? Okay, you can still ask at the end of the class, but let me just go to my presentation now. Okay. I'm presenting now this is a cycle. This is a refrigeration cycle we considered last time. We have the compressor compression. So it's 1 to 2. Then we have in the condenser, the refrigerant is condensed from 2 to 3. And then it is throttled from 3 to 4. And then it is heated or evaporated from 4 to 1. So this is the cycle. These are the components. This is the cycle that we mentioned. And as we mentioned that the ideal cycle state x1 is equal to 1, x3 is equal to 0. And then we consider the irreversible process where we have irreversibility. So 1 will go to 2a rather than 2s. And then this is what we covered in our previous class, and we have an example, 2 examples in that. I just want to introduce another diagram. We will not use it much in this course, but it's very important to know it. This is a graph that's normally used by air conditioning engineers, and therefore it is called pH. It's just the difference here. We have this is TS diagram. This will be pressure enthalpy diagram. So we are taking the 2 axes here are enthalpy and pressure. Now I just want to show here what we are presenting. So 1 to 2, this is a constant pressure line, will be something like that here. So this is a constant pressure, will behave at that, and therefore we reach from 1 to 2. Then this is of course isentropic, and this is also the irreversible process. Then from 2 to 3, this is constant pressure. So it is easy to show it here. Constant pressure is a horizontal line from 2 to 3 like that. Then we have 3 to 4. This is expansion. It's an irreversible process, and therefore from 3 to 4. So now this is here constant enthalpy. So we present it as a vertical line. This is constant enthalpy. It shows in the test diagram like that. Here it shows as a vertical line. Then 4 to 1 is another constant pressure process. This one here, 4 to 1, constant pressure process like that. So this is what you can see here. It is being simplified because I have 2 constant pressures, so they show as horizontal line. So it will be 1, 2, 3, and 4. As I now this figure will not, this diagram will not ask you about it, and but I just wanted to know when you go to an air conditioning course or refrigeration course 400 level, then they use that. Also the engineers in air conditioning and refrigeration, they use this chart more than the TS diagram. So this is also you want to learn it, but you will not be asked about it. We will always ask you on the test diagram and the flow diagram. All right. Now I want to consider 2 cases here as heat pump operation in heating mode or heat pump operation in cooling mode. You have the air conditioning unit at your home, and you use it in winter and use it in summer. And the question here is, how does it work? Just change, flip something, or it is being automatic now that it changes from heating to cooling or cooling to heating. And the difference is this here. Let us look at this diagram. So this is a heat pump operation in heating mode. In heating mode means that you are sitting inside here and you want some heat to come to you. So this is here is the air conditioning unit in winter. And this is here for the cooling mode. You are sitting here and you want to get cool air from atmosphere. So what happens here is that let us consider this first, explain it. So this is the compressor, and the compressor here, it takes out from the it goes out from the compressor to the valve, and then this is just a reversing valve, and then it goes to the condenser here. Out of the condenser, it goes to the throttling valve, and this is like the refrigeration here. So it takes heat, it gives the heat from this. So this is here in summer. This is the cooling mode. In winter, we use it to cool this place. In summer, this is the other side. What we do here is just we do not change. You know, you have a fan inside, and then the compressor is always sitting outside. So we have two states here. This is a fan, and this is a fan. What we do here, we do not change we do not change the equipment, but we change the cycle here. So in this case here, this works go to reverse it here, and then this will go to the cooling, to the heating mode here, so it gives you the heat here. So this is a condenser in this place, and this is here is the evaporator. And this way here, this is, we consider this as the evaporator, and this is as the condenser. So what we do is to reverse the cycle such that while the condenser, you change the condenser to the evaporator, you change the evaporator to the condenser. And this is what happens here. Okay, so this is explains how we use the air conditioning unit in summer and in winter, in winter and in summer, but just changing the cycle here, and this cycle will, what we are doing here is exchanging the condenser with the evaporator. So this is we reverse the process here, such that this will be work as a evaporator and this work as a condenser. But we are sitting in the same place. So if this is here, you are talking about summer here. So this is being evaporated here. So heat will be taken from this. So you will be sitting here. And then this is what happens here. Then if we reverse this here, then this will be the condenser. While you are sitting in this place, when this is a condenser, this will give you the heat here. So this is what we do here, is to interchange the condenser with the evaporator by changing the function of this here, by recirculating, by reversing valve here. So instead of going to the compressor, so after the compressor, it goes to the condenser here. After the compressor goes to the condenser outside now. So this is the condenser here. This will be the condenser here. The condenser here will give you the heat. The condenser here will throw the heat to the atmosphere. So we are sitting in this place. When we reverse this, this will be the evaporator. So in this case, we take heat from the place we are doing. So this is how the air conditioning works. While you are sitting in your place, you just change a dial, and instead of heating, it will be cooling, or the other way around. Okay, so this is, I'm talking still about a heat pump. What's a heat pump here? A heat pump works, this is a house, and then this is a evaporator will be at outside, and it takes heat from outside and presents heat here. So this works the opposite to the refrigerator. So this takes the heat from atmosphere. This is a cold place here, and when I'm talking about in winter now, so this is cold and you want to heat. So the heat comes here and then goes to the inside the room, and we are sitting here, so we get the heat from that. If this is work is in summer, then we reverse the condenser and the evaporator, and therefore this will be the evaporator. It takes the heat from here and then throw it to the atmosphere. So this is the way around here. So this is like a house here, and this is being heated. Okay. So this involves the evaporator. Okay, let me say it again here. So this is now the evaporator, which is this one here. And then the evaporator takes the heat from the atmosphere. And then this is the compressor, to the compressor as in the other cycle. And then it goes to the condenser, and then the expansion. So it are the same units used for heat pump or for refrigeration. In this case, for the heat pump, of course, we are interested about Q out here. So this will be QH over W, and this is the coefficient performance, and this will be H2 minus H3 over H2 minus H1. So this is in the condenser, and this is here in the compressor. And of course, if you consider Carnot coefficient performance, this will be TH over TH minus TC. So similar to the previous one, the only change here is that is QH over work, rather than for the refrigerator, it is QL over work. Okay. This is an example on the heat pump. So this is the same problem that we have, the same example that we have earlier. So this is here is TH at around 20 degrees centigrade you want, and this is here, it is very cold outside, as 5 degrees centigrade here. And therefore what you need here is to transfer heat from outside, which is cold, and then to inside the room. He's giving us the end states here, 1, 2, 3, and then we want to solve this and get the coefficient performance. So now we apply this equation here. So H2 minus H1, this is in on the compressor. So 1 minus 2 for the compressor. This will give us the compressor work. Then remember also the answer here is in kilowatt, not in watts and not in megawatts. Okay. Then we have the heat transfer to be provided in the building, which is Q out. This is the useful out that we're looking for. And then we have this will be H3 minus H2 minus H3. So this is the amount of heat exchange, and this will be Q out. Then we divide this, we calculate that. This also will come in kilowatt. Then we take here and get the coefficient performance, divide Q out or QH over W, and this will give us the value here. Remember also these values are some sort of values like that. Of course, for the heat pump, it cannot be less than 1. It has to be more than 1 because it is the coefficient performance for refrigerator plus 1. So this will give us this value. And then if you take here WTH over TH minus TC, then you can calculate the maximum value you can reach, and of course we cannot exceed that. So this is here based on the Carnot cycle, and this is based on the actual cycle. Getting the enthalpies here, I'm sure that you can do that because it is easy part as we have in the example before. Okay. Now we'll go to another issue here. Are you with us, Shabab?
Yes.
Okay.
Yes.
So I'm talking about now other refrigeration cycle. We have considered the simple cycle. And the simple cycle is here. This is the simple cycle. Let me look at this here. 1, 2 through the compressor, and then condenser, throttling valve, and this is evaporator. So this is one cycle that we considered in our previous part of the chapter. This is what I'm going to cascade refrigeration system. In some locations here, we want to have this is very low temperature, and sometimes the room temperature is very high. And therefore, we cannot run one cycle at a time, but what we do here is what we do cascading here, use 2 cycles here. One will go from minus 40, for example, to 0 degrees, and the other cycle will go from 0 degrees to 40 degrees centigrade. Let me get something here. Let me say this in Arabic. Sometimes you see this racing or swimming. They have, because the distance is long, they have running or جري لمدة مثلا 10 miles or 10 kilometers. And no one can do this by himself. But what they do is to choose 4 persons, for example. The first one starts, and then it gives the flag to the second one, it gives the flag to the third one, and it gives the flag to the fourth one. So we have four runners or 4 swimmers. They do the whole stage, and this is what we call cascade. So someone do part and gives the flag to the another one, give it to the third one, to the fourth one, and so on. So this is here what we are doing because the distance is long. Here we have temperature is very wide here. So I may have from minus 40 to 40. I cannot have one refrigerant doing this. Will need a lot of work, and it has to be, remember, it has to be in the vapor or in the liquid form. It cannot be in the solid form. And therefore, we use 2 cycles here. Okay. Is my introduction clear? You know what I talked about swimming and running, racing? Is it understood that I have long distance? I mean, one cannot do that. So what we do is to take, for example, Hassan, Bakr, Mubarak, and then make a team. Hassan will take the first period, first 2 kilometers. Ali will take the second 2 kilometers, and so on. So we are working together as a team to do the job. This is exactly what we do here. We have this cycle. We'll have from minus 40, for example, to 0 degrees centigrade. So it takes the heat from the very cold space, and then throw it away to here. It does not go to the atmosphere, but it goes to the other fluid here. So this here works as an evaporator. This is a condenser for this cycle. This is an evaporator for this cycle. And this will do the same here and throw the heat to the atmosphere here. We normally use this when we have, for example, If any one of you knows that we have some materials that we plant in winter and want to keep it in summer, so like potatoes, for example, or uh, any other vegetables that we want to keep from one season to another, then we keep it in a very cold place. Also, we have the ice skating. The ice skating requires very low temperature here. So what we do here is that we cannot have one fluid to try to work between -40 and 40. Because it may be, if it is vapor here, it may be solid here, and this is of course not acceptable to flow. And if we have even one fluid, then it will have a lot of work because we are going here compression very long from low temperature to a very high pressure here. So it takes a very large amount of work. So this is what we call cascade refrigeration cycle. Cascade is that one will give one cycle, will give to take the heat, transfer to another cycle, and the second cycle will transfer it to the atmosphere. So this is just two simple cycles. You work with this cycle here, and then the Q comes here, give it to the evaporator, and then it comes like that. So this is, you solve it, this, don't complicate things. You solve it as if it is two simple cycle. And this is one of the easiest cycles that you have, and this is another easy cycle, but just the connection here, this is what you have to take about here. So what we do here is that we run the cycle. If I know the mass flow rate here, I run the cycle and then get Q dot here. Then I use this cycle here with this Q dot and use it in this cycle here to get that. So what we do here is two things. I want to calculate QL here. So what is the refrigeration when I ask about the refrigeration capacity? This is a QL here. This is the refrigeration capacity. So it will be the mass flow rate of P here multiplied by H1 minus H4. So this is the refrigeration capacity that we have. Here, this is internal here. We do not do anything with that here, but just for the mass flow rate. But if I want to calculate Q out, so this will be the mass flow rate of A, H6 minus H7. And the work done will be both of this here. This is H2 minus H1 multiplied by the mass flow rate plus H6 minus H5 multiplied by the mass flow rate here. So we have to calculate the power for this compressor, and we add them together here. So this is we need to calculate the refrigeration capacity from this equation here. To calculate the work, I have to get here H2 minus H1, but multiplied by the mass flow rate. I have to get it this in megawatt or in kilowatt, sorry. And then calculate this in kilowatt and add them together. You cannot say H2 minus H1 plus H6 minus H5. This is not correct. You have to say here the mass flow rate of A, H6 minus H5, plus the mass flow rate of B, H2 minus H1. Then this is kilowatt, you add it to this kilowatt, and this will be the total amount of work that we have used. Then divide QL over this amount of work, Q dot L, also in a kilowatt. And then divide by this get the coefficient performance. Then there is a relation here. This relation here, it decides how much mass here with this mass. Normally in a problem, we'll give you only one mass flow rate, either this one or this one. And then utilize the balance here, the energy balance here, to get the second mass flow rate. So I'm saying here that M dot A, which is this one, H5 minus H8, will be equal to M dot B multiplied by H2 minus H3. So this will forget about the signs now. It is just a quantity here equal a quantity here. And this will give you the mass ratio that you are looking for here. Then, so this is what we do here. And the way here that we go from 1 to 2 and then cool and go on, this was, so we save this amount of compressor work. So the reason why we use the cascade refrigeration cycle is that we save this amount here, even if we can have one fluid goes from -40 to 40, but even if we have this fluid, then we will save a lot of work here. But most of the time we cannot have a fluid that's from -40 to +40. It will give us so much work here. Okay, شباب.
Yes.
Okay, it's clear here. I don't want to complicate things. It is two cycles. We just get them together here and the only link here, this is the flag here. The flag is given from this fluid to this fluid, which similar to the runners or the swimmers and so on. So this is one modification here, and this is required when you have very large temperature difference. This from this look minus 40 to 40. Normally we work from minus 20 to 20 here to the atmosphere around, but this is here, if this is very large temperature difference, then we have to go with cascade refrigeration system. Okay, another modification that we use here is what we call multi-stage compression refrigeration. This is also to avoid to overcome the problem of very cold and very warm place. So what we do here is that we have a fluid here, and this is condensed, and then out of the compressor it is condensed, and then we have a flash chamber here. Flash chamber here, it works as it separates the gas from the liquid. So this is a throttling process, and then this will give us here liquid. So this is 5 here. When you throttle 5, this is you have liquid and vapor here. So you separate the vapor, which is 3, and the liquid is 7. So when you have a throttling process from 5 to 6, then you have gas and liquid. This is what we do in desalination plant. Suppose you get water from the sea, and then you have it at this high pressure. When this is the water from the sea, it is, of course, it is salty water. Then what you do here is throttle it like that. Then you take the vapor, and this will be distilled water. This will be the vapor without salt, and then this will be with much salt, enriched salt here. So you take, this is the fresh water here, and this is, you can do this again and again here, so you can throttle again, you get the gas, the vapor, and then you get the liquid and do that. So this is the desalination plant work like that. You have at state 5, you have this is salty water, you throttle it, then you take the gas, the vapor, so this will be the fresh water that you can drink, and this will be, you throw this away or you make another cycle with that. So this is what we call the flash chamber, changes the vapor from the liquid. Then you take the liquid here and pass it to an evaporator, to a compressor, then we mix this together and come back to the high pressure compressor and the same as this one here. So this is a cycle here. We have from 1 to 2 compression, and then 2 we add 2 to and 3 here to get 9. Then we compress 9 to 4, then condense it here 5, and then this is split it here, the gas and liquid, and then we take the liquid and pass it here, and the cycle continues like that. So if I want to calculate QL is this place here. So it's H1 minus H8. But with the mass flow rate, if I have M5 has X in this direction and 1 minus X here. So the mass flow rate here is 1 minus X multiplied by M5. Then I multiply by H1 minus H8. And then when I do the mixing here, I have 2 here, so state 2 here, H2 multiplied by 1 minus X plus H3 multiplied by X, and this will give me M5 multiplied by H. Sorry, this is H9 here, so I have to change this to H9, and then you have H9 here, so you mix 2 and 3 to get H9. So please, I will correct this in the notes here to be H9. So this will be, you mix 2 and 3 to give you 9, and then the cycle continues like that. So this is another cycle, but it's not much used as the cascade cycle. So I will not ask you, this can come in the homework, but in the exams, I will avoid this cycle. And then this cycle, this is easy to do. It's just 2 cycles here. So this you will be responsible for this in homeworks and the exams. And this you will be responsible only in homeworks, not in exams. This part here, this is also used for multi-purpose refrigeration system, and I will bypass this, so it is deleted from the course. And also liquefaction of gas, this is also works for when we have the air and want to separate the oxygen from nitrogen, then we cool it very low temperature, and then we separate the nitrogen from the oxygen. And another application here, okay, this is, I'm considering this here, gas refrigeration cycle. So this is here, I'm going to consider that. So let me just summarize what I have mentioned today before I go to the next part. Okay, what I mentioned today is that I'm talking about a heat pump. How do you change from, okay, how do you change from air cooling to heating? This is one topic I mentioned. And then we consider the heat pump, how to solve a problem on a heat pump, and then calculate the coefficient performance. And then this is an example here. Then I went to the other issue here, that we have a cascade refrigeration cycle when you want to have refrigeration or air conditioning between very low temperature to a very high temperature, and this is, you are responsible for this part. This I explained, it may come in the homeworks but not in exams, and this also will not include in exams, this will not include in exams. So this covers vapor compression cycle for this chapter. Now another topic here is gas refrigeration system. In the aircraft, we use gas refrigeration system. What's gas refrigeration system? In this case here, we use gas rather than refrigerant here. So we use this as a gas rather than refrigerant. So in this case, we can use the ideal gas and so on. And this is a reversed Brayton cycle. So this is here a reversed Brayton cycle. So this is, remember, this is a cycle, Brayton cycle like that. We are reversing Brayton cycle 1 to 2, and then 4, 2 to 4, 2 to 3 to 4, 5 and 6, and to 1 again. So what we are doing here, this is a gas cycle, and it works as a refrigeration cycle, but we are using a gas here and not a refrigerant. So what happens here is that we have this is the heat exchanger, and this is the cold refrigeration space here. This is the refrigerated space, and then we take the heat from that. So this is the heat exchanger, and which is this part here. So this is from 5 to 6. QL will go into this part, and then from 6 to 1 we have, this is from 6 to 1. Then we have here a heat exchanger, and give it to the compressor. The compressor will compress this from 1 to 2, and then from 2 it goes to 3 heat exchange. So this will throw this away, or if you are using this as a heat pump, so will be sitting in this place. This is warm place, and then it goes from 2 to 3. Then we have exchange heat from 3 to 4 again to the turbines. Because this is a gas here, then in this case here, we do not throttle this, we do not use the throttling process, but use a turbine to give us some work. So in this case, this will be QL, which is this amount here, divided by W net. W net is W compressor, but we subtract W pump here because this is works as a turbine, so this will take W net from here. This is why, because this is a gas here, whenever we use a gas, then it is better to use turbine, because you know this will give us much work. So this work will be less now with the gas refrigeration cycle. Okay. So it is, I can use a simple cycle here. This is a cycle now. This is exactly a reverse Brayton cycle. So this is 1 to 2, 2 to 3, and 3 to 4. You solve this as a Brayton cycle, but just reverse. So this is a compressor now. So the compressor here from 1 to 2. Then you calculate from 1. 1 will be given, of course, to us. Then you calculate 2, and then you get the compressor work. Then it goes here to the heat exchanger, and this is throw heat away from the system. This will be 2 to 3, so calculate H2 minus H3. Then it goes to the turbine. Instead of a throttling valve here, we use a turbine. So this will go from 3 to 4 in the turbine. Then this is the heat exchange in this location here. So this will be the simple cycle, what we call Brayton refrigeration cycle. It is a reversed Brayton cycle, and use a gas here. So if this is air or any gas, then you are going to use ideal gas relation. So in this case, you can say CPT2 minus T1, CPT2 minus T3, and so on. So you can change delta H to work as delta T. Okay, so now we have a process 1 to 2. Process 1 to 2, it is compression in the compressor. This is an ideal gas, as I mentioned, so you treat it as an ideal gas. Get it from the table, PR, and so on, or use constant circuit CP delta T. Then it goes from the compressor changer. Then, so this is here, throws heat to the to the atmosphere. This is in place heat exchanger, in place of the condenser in the refrigeration cycle. Then it goes to a turbine here, and this turbine is used rather than a throttling valve because the mass rates here are large and therefore to produce some power. Then it goes to the heat exchanger here, which is replacing the refrigerator, the evaporator in the refrigeration cycle. So the heat will go from here to the heat exchange and then to the heat exchanger and then go to the atmosphere. So this is what we call a Brayton refrigeration cycle. It's exactly similar to Brayton, but it is a reverse cycle. And the work here will be equal to W compressor minus W turbine. And of course, this will be QL. If this is for cooling, so you call QL over W. If this is used for heating, you use, say, Q out over W. And this is the one that we use in the cabin of an aircraft. We use reversed Brayton cycle. Okay. So now we have, this is here, H1 minus H4. This is the refrigeration capacity over W compressor minus W turbine here. So this is here H2 minus H1 minus H3 minus H4. Okay. This part is deleted from the course for all sections. This is not considered. This you will consider in another refrigeration course later on. But this is not, this is outside of the course. So we have deleted this cycle. Although it is very well known and most of the large refrigerator use it, but we give it in 400 level course. Also, this thermoelectric is outside our coverage in the course. I put this as deleted and excluded in the syllabus that I give to you. So with this here, I'll end this chapter. And then I think we are going on schedule now. Only Sunday will be off because we have the quiz and also Monday. So with this, I end my class today. Any questions? شباب؟ شباب؟
دكتور معنا بس كاسكيتد وجاز ترباين.
Yes, so you have what I mentioned today is this is Brayton reverse cycle. This is one part, and the cascade cycle. This is the only part. This is you are required to know that this cascade. Then this you should know this, but I'm not going to get this in exam, and also this one and this one. Okay. So the cascade cycle. This is one of your responsibility in this course. Okay, Shabab? Which is this slide here. I will probably upload the slides today because we finished the chapter, so I'll upload the slides. So this will be available to you all the presentation for this chapter here. I will upload it today, inshallah. Did I answer the question? So for your question, cascade refrigeration system is major part of your of this chapter, and this can be included in on homeworks and exams. Yes. Other question? Shabab? Let me take attendance. I have 29, still 2 students are not available here. Okay. Okay, I took the attendance now. If you have any questions, if you want to leave, that's fine. Shabab?
دكتور
Yes, please.
الحين الفرق بين البرايتون والبرايتون ريفيرس لانه هو الإيفابوريتر عكس ابدله بالكوندنسر بس.
The gas refrigeration cycle is exactly the reverse Brayton cycle. So when you solve a Brayton cycle, it is clockwise. When you solve reverse Brayton cycle, it is anti-clockwise. But the way you deal with delta H and the same, everything is the same. but it seems like the compressor in the place of the turbine in the place of the compressor. But we deal with it exactly as the Brayton cycle, except that it is reversed and we give work rather than taking work. Yes. I'm listening يا شباب. No questions? No questions, and I'll see you Sunday, inshallah. And yes, as I mentioned in the beginning of the class, the quiz you will, as I understand, I put it in the blackboard. If I'm correct, then it will allow you to have one question by question, and then you have 10 questions. So make sure that you solve all the 10 questions. The numerical parts will have more weight, 2 points. The statement parts will have 1 point each. So I have 4 multiplied by 2, so it's 8, and the other 6 are statements. Everyone have 1, so this will be 14, and it covers all chapter 9. It's only on chapter 9, and it covers all chapter 9, including the aircraft, the gas turbine for aircrafts. Okay.
Doctor, is the assignment included?
The assignment is included, yes. It is part of chapter 9. And I already posted the solution, huh?
Yes.
Yes, some of you have done it correctly, but many of you did not do it correctly. But I already posted that, and I already posted also homework 4. You asked for it, and I think you told them about that, Hassan. Thank you. Any other question, Shabab? So I will count up to 3 and then I leave.